Chapter 4, Section 4 is called the Proving Triangles Congruent by SSS. Most important today, SSS is what stands for side, side, side. Side, side, side. That's exactly what SSS stands for. So you're going to see it written as SSS over and over again. I'll talk about what it means, but what it stands for is side, side, side. The exact same word written 3 times. So we can prove triangles congruent with something called side, side, side. And this postulate, again, I don't care about the numbers. Don't give me the numbers. It's not important. What I do care is that you understand that there's something called the SSS, or side, side, side postulate. And it says if 3 sides of one triangle are congruent to 3 sides of another triangle, then those triangles are congruent. Meaning you don't need to actually show that 3 sides of one triangle are congruent to another and 3 angles are congruent to another. It is enough to show that if I've got one side matching one side, a second side matching a second side, and a third side matching a third side, then it is a guarantee that these triangles are congruent. And we actually saw this when I did the pens. If I take 3 pencils, first of all, I just grabbed 3 random pencils from my cup over there. They're all of different lengths. They've been used, they've been sharpened, so they're all of different lengths. If I were to put them together and form a triangle, I am limited. I can't choose whatever size triangle I want. Those three sides will guarantee make the same triangle. If I were to hand you these same 3 pencils and you put them together end to end, you would end up making the exact same triangle. I'm not playing, I can't move the angles anymore. If I do, then they won't be end to end. So side, side, side is enough to say that they are congruent. You actually don't even need to prove that the angles are congruent. All you need are 3 sides of one matching 3 sides of another, and that is enough by the side, side, side postulate to prove that 2 triangles are in fact congruent. All right, so let's make a decision here. It says decide whether the congruence statement is true. Explain your reasoning. So it says triangle DFG is congruent to triangle HJK. So let's make this determination as to whether they are congruent. Gio?
Yes, they are congruent.
Why?
Because of the SSS postulate.
Okay, so he's saying the side, side, side postulate. Let's just do one thing, though. Let's verify that this congruency statement is actually true. Because remember, we said that the congruency statement says that it shows you which pieces match up. It's saying that DF and HJ are the same pieces. Let's just check that. DF, HJ. Okay, those are definitely congruent. They match each other. I'm also going to check the others just to be sure because they might actually be congruent, but this might be the wrong congruency statement. Here is FG and JK. FG, JK. Those 2 match up. That's great. So far, so good. And then finally, the only other combination is DG and HK. DG, HK. They match up. So guess what? These 2 triangles are definitely congruent by the side, side, side postulate. So 3 sides of one match 3 sides of another. Therefore, it is a guarantee that these triangles are congruent. Okay, decide whether the congruency statement is true. And then we're going to explain our reasons. Like they're saying that triangle ACB, the one on top, is congruent to CAD, the one on bottom. What do we think? Susie?
No.
Why not?
Because side CD is 4 and side AB is 3, so they don't have the same side. Like it's not the same side, so it can't be true.
Okay, so congruent means same shape, same size. And here's the things that are true. 7 matches 7. 9 matches 9. But that other side doesn't match the other side. They only have 2 sides that match each other. The third side does not. So in fact, these are not congruent to each other. That is a guarantee that they are not, because when 2 things are congruent, it means they are the same shape and same size. Same shape, same size. And one of the ways we can prove that is with SSS. So you can see how quickly this goes. Decide whether the congruency statement is true. Explain your reasoning that triangle QPT is congruent to triangle RST. Gio?
Yes, because of the SSS postulate.
Okay, so let's just check this just to sure. He's saying SSS for sure. The picture certainly shows SSS, but let's also check the congruency statement. They're asking us whether the statement is true, not whether the picture is true. So let me just check here. QP is congruent to RS. Here's QP, here's RS. Those 2 match up. PT and ST. Here is PT and here is ST. Those, in fact, match up. They have the same congruency statement. And then QT and RT. QT and RT. They match up as well. Side, side, side. They are congruent. So this is just one of the ways that we check. But it did ask me to check the statement, not the picture. So the picture, yes, they are congruent. And the picture matches the statement there. And that's what we're checking is the statement. Yes, ma'am.
I'm confused on how do you check the statement?
Well, like the statement, when we look at this, it shows, remember we learned that the statement shows which angles match up with which angles and which sides with which sides. It says that angle Q is congruent to angle R. It says that P is congruent to S and T is congruent to T. But it also shows us which sides match up. So let's say I wrote this out as triangle QPT is congruent to triangle SRT. Well, you might look at the picture and say, well, of course they're congruent. Look, it's got side, side, side. But we have to check the statement because it says that in the new way that I wrote it, this is just me making stuff up here, QP would match up with SR. QP is this one right here. SR is, I just did the same thing, didn't I? I just reversed them. I didn't mean to there. Here, I'll call it, how about TRS? There we go. So QP matches up with TR, matches up with that one. So the congruencies, even though the two triangles may be congruent, it's the wrong statement. You know what I mean? Is I matched up the wrong parts in the statement. Whereas theirs is completely fine. Theirs matched up exactly like it should. Yes, sir.
If you had QPTs congruent to SRT, wouldn't it not be congruent because Q and S aren't congruent?
Well, what I'm saying is that one of them is a statement. They're asking me to make sure the statement is true. The picture is definitely true. These are congruent triangles looking at them. But I need to make sure that what I'm saying matches the picture. And that's what we're doing is we're checking the statement. Does the statement match the picture of which things are supposed to match up? So that's how we're checking it. So again, tonight's homework is actually not due until Friday. So I'm going to stop at this slide, leaving only 2 extra slides to do for tomorrow. We're going to hit 4, 5, and the last 2 slides of this tomorrow. But you could probably get a lot of tonight's homework done just based on that. I've given you everything you need for it. Picking up where we left off yesterday is we had the side, side, side postulate. Remember, side, 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 that if 3 sides of one triangle, remember this is for triangles, not for other shapes, for triangles, are congruent with 3 sides of another triangle, then those triangles are definitely congruent. You don't need to actually prove all the angles as well. It's just one of the many shortcuts that we are going to learn. Okay, so here's where we left off. JKL has vertices of -3, -2, that is here, 0, -2, that's here, and -3, 8, -3. -3, -8. Oh, that's kind of annoying. That's off the grid here. So like right there. Okay, so this triangle looks like this. Here is J, here is K, and here is L. And then we've got, our triangle is going to look something like this. Now, some things I know about this triangle right away is I know that this length up here is 3. I know that because I could just count across horizontally. And I know the one on the left side is 1, 2, 3, 4, 5, 6 units long because I can just count vertically. What I cannot do is count diagonally. So I'm missing that last side there. But I'm going to look at the other triangle. We've got 10, 0 is here. That's R. We've got 10, -3, 1, 2, 3, that's S, and 4, 0, 1, 2, 3, 4, 0. Okay, so this triangle looks like this. I'm going to change color so it shows up here since it's on the axis there. Okay, so we've got 1, 2, 3 units here, 1, 2, 3, 4, 5, 6 units here. So this is not enough yet to prove that these triangles are congruent. We have a side that matches a side on one triangle matches the other triangle, one side, another side matches the other side on the triangle, but we're missing that third side. So how is it that I am going to be able to figure out whether that third side is congruent or not? Unfortunately, it's the distance formula. So let's do this one over here. And the distance that I need here is this side over here, the one that goes from K to L. So I'm going to look at the points K and L here. K is 0, -2. L is -3, -8. And I'm going to do the distance formula between those two. And just so you see where I'm getting my numbers from, I'm going to do x1, y1, and x2, y2. The distance is equal to the square root of x sub 2 minus x sub 1 squared plus y sub 2 minus y sub 1 squared. Do a little plugging in here. -3 minus 0 squared plus -8 minus -2 squared. And we get -3 squared plus, this becomes -6 squared. And we get the distance is equal to 9 plus 36, or the distance is equal to the square root of 45. In simplest radical form, we can do that as 9 times 5, square root of 9 times the square root of 5. One of those two breaks down. Which one?
9.
9 into what?
3.
3, square root of 5. Yes, sir. You could put the y's first, but the y's have to be grouped together. And if you do y2 minus y1, then you have to do x2 minus x1. I wouldn't mess around with the formula too much, because then people start getting into the, like, well, can I do this with the formula and can I do that? And like, there's lots of things you can and cannot do with it. So I always just say, just stick with the original formula. Then you don't have to remember which ones you can and which ones you can't. So the distance here, the length of this line is 3 square root of 5. I need to check the other one. It better be 3 square root of 5. So let's take a look. We've got the points S and T because we're looking at this line here. S is 10, -3. Bless you. T is 4, 0. So the distance is equal to the square root. I'm going to do x sub 1, y sub 1, x sub 2, y sub 2. X sub 2 minus x sub 1 squared plus y sub 2 minus y sub 1 squared. I tend to write that over and over again because it means that I know exactly when I look up exactly what I should be putting in there. So I've got 4 minus 10 squared plus 0 minus -3 squared. -6 squared plus 3 squared. These numbers look very familiar to me. D is equal to 36 plus 9. The distance is equal to the square root of 45. I already know they're congruent to each other because we've already had the square root of 5, which breaks down into 3 square root of 5. These are definitely congruent by side, side, side. But what was hard about it is finding that third side, proving that the third side was congruent. Two sides, there's no such thing as third side theorem. So don't do that. Because two sides are congruent, the third one is congruent. That's not something we've got. Yes, ma'am.
So when you like these sides equal, there's no, like when all these sides are equal between two shapes, there's definitely no possible way that they could not be congruent.
How about we say it the other way? If 3 sides of one triangle are congruent to 3 sides of another triangle, it is a guarantee that they are congruent. Guaranteed. All right, so here's where we get into a little construction. I'm kind of sweet on this problem. Other math teachers I know don't like it because this is an actual real-world problem. It says, explain why the bench with the diagonal support is stable. So they're saying the one on the left is a very stable bench, while the one on the right is the one that can collapse. Okay, so let's talk about the one on the right first. If you've ever had a cardboard box, like a cardboard box that you've opened up, like an old cardboard box like this. Okay, just imagine a cardboard box. You just got it, like you're a kid, you're playing with it, like your parents gave you this old box, whatever. They're like, yeah, for sure you can play with it. and I push down on the top of it, what happens to that box? Yeah, it kind of like slips, right? It does this. It kind of like bends like this and starts to get crushed, right? It has no support on the inside. It can wobble back and forth. Like if you push it on the top, you can slide it to the left, you can slide it to the right. It doesn't hold its shape very well, correct? And that's why when we build things, I don't know if I've told this story before, but one time I decided to build a gate for my house, and unfortunately I didn't think about it, and I built the gate like this. I built a giant rectangle, and then I put those little, the wood planks on there to make it look like a fence. And actually, it was an awful gate. It was an awful gate. I didn't think about it. I didn't know much about building gates. I just figured, I could do this. I know how to use tools and stuff. And I was like, oh, okay, this is not a problem. But let me show you why that is such a bad idea as compared to this. So we already know, just like the box, that if you put weight on this, it can shift to the left, it can shift to the right. But here's the thing. So let's look at this bench, and we know that when we build a bench like this, that when we look at this line here and this line here, would you agree that when we build a bench, we build those so that they have the same length here? Now, granted, this sticks out a little here, but I'm just talking about this distance right here. Would we agree that they're the same length there? Okay, so the top and the bottom are congruent. And would you agree that the left side here needs to be the same height as the right side, or it's not going to be a very good bench? Right, it's got to be the same height or else it'll be slanted. And lastly, do we see that there are two triangles in there?
Yeah.
Okay, so we've got this one in here. This is that reflexive property. So the question is, why does this make a better bench? Why does that thing make it in there? Well, when we've got side, 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 which we do here, we have side, side, side. I shouldn't have used red. That didn't show up very well. Here's side, side, side on the top triangle with side, side, side on the bottom triangle. Those triangles have to keep their same shape. They cannot change sides. They cannot change sizes. When we've got two triangles that have side, 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 what happens is they are forced to be the same size and same shape. Whereas this one could bend a little. It could actually, like when two people sit on it, it could kind of shift like this and start to collapse, because it doesn't have any support in there. These triangles are forcing the other triangle to be the same size. One triangle can't move without the other. The triangles have to stay the exact size. So this is why, when you see in construction, why people build things like that with that diagonal in there. Because it keeps the sizes. It means when you build them in a roof, your roof isn't going to move. Sure, a hurricane could rip it off or whatever, but it's not going to move just naturally from the wind or anything like that. So just an idea of where that comes from in there. We're going to move on to 4-5, the next lesson.